All right, so I hope that my video is clear enough and my sound is clear enough. And right, so yeah, I just want to continue where I left off before, which is the 2.4, which is the master, right? So yeah, the GFS architecture is inherently like a single master, which I think it mentioned before that it is largely simplified the architecture, which is actually a very sensible thing. Yeah, nobody wants to like maintain multi-master, complicated synchronization and stuff. Okay, so let's say Fastly. Look at this. They highlight that this is vastly simplified their design and enable master to make a sophisticated charm placement. Uh, I don't know what's the relation between this simplification and this sophisticated. I think I do know like what prevents them from making sophisticated charm placement if they are like doing a bit more complex architecture. But yeah, let's move on. And replication decision using global knowledge. Yeah, basically it's single notice is always, and not saying it's easy, but like way easier than managing multiple nodes and trying to do like global synchronization and stuff. However, we must minimize its involvement in reads and writes, because yeah, that it does not become bottleneck, of course, because yeah, everything that goes through this GFS master, if it has to be like that, then like it like become a proxy to accessing the file, which is not something that we want, obviously. Not something that they want. Is that's going to be bottleneck? Okay. Client never read and write data through master. Like in a sense, the chance server is the chance servers are exposed to the network with the client. Like it might work for internal tools where you know that they are the client is like where it's going to well behave. Actually no, actually not necessarily. The client could just cross like overload the chance server, maybe even it's for internal tools. Yeah, it's actually just not really guarantee, isn't really guaranteeing. Anyway, so instead client asks the master which chunk server it should connect. It's like DNS stuff. It caches this information for a limited amount of time and interact with chunk server directly for many subsequent operations. So I think at a certain point, like the client will have the knowledge to like every chunk server is available. Like if the client is really making a high throughput writes, and maybe the GOS the master will like distribute the request. Okay, so let us explain the interaction for a simple read with reference to figure 1. I think it's clear enough, but let's just read it anyway. First, the fiction size. Using the fiction size, the client translates the file name and the byte offset specified by the application, which means the client, right? In the chunk index within the file. Okay, so like given a file, right? This is a file. The application, the clients, which will like create an will split it internally. The client will, and like it's going to be good chunk 1, chunk 2, chunk 3, like this. Maybe it sent the master a request containing the file name and the chunk index. So like this is index 0, x1, x2, and this is defined by the client. Is that correct? Right, the master you see the client translate. Look at this, the client translates. So this translation is made within locally in the client. So it's not like the client uploads the entire file and then like behind the scene TFS will like split them. Yeah, that's what it's like they're trying to avoid. They want to try to avoid the directly operating the file system, like doing file operation through the master. So they don't want to do that. Oh, it's okay. The master replies with corresponding chunk handle and the location of the replicas. So okay, I'm going to upload this file which is like complete to the file chunk. Okay, and the server going to say like, okay, here we go. You can put it there, and there, right? The client sent requests to one of the replicas, most likely the closest one. Okay, and the request specifies the chunk handle and the byte ring within the chunk. Okay, so chunk handle. What is chunk handle? Handle is like an ID, right, basically, and byte range within the chunk. Byte range. So say this is right. Okay, this is it. Alright, so further reads of the same chunk require no more client master interaction. Further reads, you mean like once I uploaded this, if I want to read back again, basically the client still have the information, right? Until gets information expires or file is reopened. In fact, client typically asks for multiple chunks in the same request, and the master can also include the information from chunks. I don't know what is information for chunk immediately following those requested information for chunks immediately. Okay, so this extra information sidesteps several future client master interaction at practically zero cost. Well, you have network costs, you have okay. Chunk size. Okay. Chunk size is one of the key design parameters. We have chosen 64 megabytes, which is much larger than typical file system block size. Yeah, because they want to optimize like big block writes. Each chunk replica is stored as a plain Linux file on chunk server and is extended only as needed. Lazy space allocation avoid wasting space due to internal fragmentation. Perhaps the greatest objection against such a large chunk file. Wait, what is it? Lazy space allocation. What is this? Where does it come from? Avoid wasting space. Like even extended, it means like they're not going to include. Oh, sorry, extended means like they're not going to pre-allocate the space for the file just because it might be written again next time, which is reasonable actually, but I think yeah, at scale that's going to waste a lot of space probably. So this is a good model. Lazy chunk offers several important advantages. Large chunks. Okay, it reduces client need to interact with the master because because read and writes on the same chunk require only one initial request to master for chunk location information. So basically asking the querying DNS thing. Okay, you basically cast it, and because it has larger chunk size, Redis client need to interact with the master because on the same chunk. Okay, so if you have like big file, basically say that it's likely that I will delete this large file. So you just put it there. Okay, so I think I'm quite I'm just saying nonsense just now because application mostly read and write large files sequentially. For smaller interprets, the client can comfortably cast all the char information for a multi-ticket working site. Yeah, it's not just metadata things, right? So the client can cast them. You can cast, I don't know, like 10,000 of small files location, and I think that wouldn't be really a problem. Metadata is very efficient. Okay, so it's very small, so I think it's fine. What is this? Reduce overhead by keeping persistent TCP connection. Okay, they are using TCP. Well, what else they want to use? Yeah, it has to be TCP. The chance saver over an extended period of time. Third, it reduces the size of metadata stored on the master. Wait a minute. Why come? Since large chunks fly more likely to perform many operations on a given chunk, then yeah, probably they already observed the behavior though. Like the way they that's why they have this kind of very big detail of what is what. Like how did they achieve this, which is very nice. On the other hand, a large chunk size, even with lazy space allocation, has disadvantages. A file consists of a small number of chunks, perhaps just one. The chunk cluster storing those chunks may be perhaps just one. Oh, I'm sorry, I'm so sleepy. I'm here eating my tiramisu. Just need a break. Alright. Honestly, I'm very sleepy right now. Let's just complete this session and like we can stop. Blah 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 blah. To reduce the size of metadata stored in master. Yeah, because yeah, because if you file like just one and like it's super gigantic, then you only have to store like metadata for that one file. Basically, that's just the logic here. Which are two important items of other that we will discuss in sections. Okay. Keep the metadata stored in memory, which is like basically like, oh, okay, you have a lot of stuff and if this is small enough, especially if like database or any system that needs to access the system, any subsystem that needs to access the entire system, it has to be like um yeah, and it has to be small. It has to be like uh being able to be just small enough so that their working set, that their work set is preserved in memory, and like that makes the accesses way faster. Yeah, that's just reasoning, which is actually very sensible thing to do, but in the same time it's like quite obvious, right? But yeah, a small file, yeah, this is if, on the other hand, large chunk size, even with lazy allocation, has advantages. A small file consists of a small number of chunks, perhaps just one. The chunk server may storing those chunks may become a hotspot if many clients are accessing the same file. But wait, a small file consists of a small number of chunks. Oh. The chunk server storing those chunks may be hotspot and if many clients are accessing the same file. In practice, hotspots have not been a major issue. Many clients accessing the same file. Okay. Basically, they are not. I think they are not really trying it. However, Hotspot did develop when GFS was first used by a batch queue system. Nextable was written to GFS as a single chunk file and then started on hundreds of machines. Wait, what? Oh, executable. Started on hundreds of machines at the same time. So it's not always like something like a file, like a machine learning file or something. Someone have uploaded executable and everyone tries to download them. Today, she chance ever storing this is roughly by hundreds of simultaneous requests. Okay, so they solve such problem by storing such executable with higher replication factor and making the batch queue system stage. Potential launch solution is to allow client to read data from other client. Okay, that's peer-to-peer. That's really interesting. The master stores. I want to continue this, but let's do it next time, man. Let's do it next time. Yeah, I'm really sleepy right now. It's like it's 9:30. 9:39. Okay, I don't know why I feel so sleepy. But anyway, I will stop. I will continue tomorrow with the metadata, which is I think it's quite long, but yeah, see you tomorrow.